For module 2, the last topic is hydrothermal scheduling and optimal power flow. Okay. For this, you won't be asked in numerical problems in your syllabus. Only the essentials of this is available. But if you do research in whether it's smart grid or anything related to the power systems, this is the starting point. Okay, the optimal power flow is the starting point of any research that you are going to do in power systems. Okay. Hydrothermal scheduling is a pretty old problem in power systems. So we have seen economic dispatch, where we have seen that for optimal operation of the system, that means for minimum cost operation, the incremental cost of the generator should be same. What is the incremental cost of a hydro generator? We have Iraqi plant nearby. What is the incremental cost of a hydro generator? What is the fuel for hydro generator? How much we have to pay for the water? It's free. The incremental cost of hydro generator is zero. Practically zero. The payment that the plant makes is only for the capital cost, the loans that have been taken. But since most hydro plants are government owned, it's also negligible. So the incremental cost of hydro plant is zero. Therefore, in the conventional power systems, of the 90s, where about 95% of the power system had only hydro and thermal, we had a 60-40 rule. Okay, we had a 60-40 rule. It was said that 40% hydro and 60% thermal will make the system stable. And the objective was to minimize the coal consumption based on the availability of water. Now the only problem with hydro generation is that water should be available. Okay. If there is no water in the reservoir, then we cannot generate power from the hydropower plants. Okay. Then hydropower plants are generally, thermal power plants are made only for power generation. But hydropower plants are just outcomes of some other project. Just like Hirakud power plant project was not for power generation. It was a multi-purpose project. Irrigation, flood control. A hydro came out of it. Okay. So for the water available in the reservoir, it is most important for irrigation, not for power generation. If it is water available is more, then only we can use for power generation. So such kind of rules has to be followed when water is to be provided to the for power generation, so that thermal power plant reduction can take place. Okay, that is one aspect. Okay. The other aspect is time period. For example, we have seen that thermal power plants we do scheduling for on hourly basis. We say rupees per hour, something like that. But hydropower plant cannot be scheduled for hourly basis. Our constant here is not how much power, how much water is available per hour. Our constant is how much water is available for generation during a day, minimum. At the least time period of time, you can say resolution, minimum for how much duration for one day, how much water is available. Then we have to divide that across various hours. So hydropower scheduling is a multi-time period scheduling problem. That means, therefore, it is very difficult. For thermal power plant, you are only scheduling for 1 hour, whereas for hydropower plants, you are scheduling for, say, at least 24 hours. And based on that, we have got two kinds of scheduling problems. One is known as long-range hydrothermal scheduling. Write down these two. Long-range hydrothermal scheduling, 1 week to 1 year, and short-range hydro scheduling, 1 day to 1 week. 1 day means 24 hours. So the minimum period of hydrothermal scheduling is 24 hours. Okay. Now this long-term hydrothermal scheduling involves meteorological and statistical analysis, whereas short-term scheduling involves hour by hour scheduling for a complete day. Okay, just write down long-term hydrothermal scheduling and short-term hydrothermal scheduling. Okay. So, in your exam, 2 mark questions can be asked. What is the objective of hydrothermal scheduling? The objective of hydrothermal scheduling problem is to minimize the total fuel cost from thermal generators by optimal utilization of available water resources over a period. Available water resources. After it is used for flood irrigation, etc., what is available? Okay. The hydrothermal dispatch is usually more complex than the thermal dispatch because all hydro systems are different. The results are natural difference in watershed. What is the watershed? The area which is drained by the water body. That's the watershed. Artificial storage, control of water flow, and constraints on the operation. Okay. So, from long question perspective in your exam, you will be asked to formulate the problem. Okay. So there, what was the formulation? Minimize Ft summation Fi subject to power balance, summation generation equals to demand, and the inequality constant. But here, the additional constant is the total availability of the water. Okay. So here you will see there is an integration sign here. Why? Because for the whole time period you have to find out. Say, for example, a day. So T may be 24 hours, so you have to go for 1 hour, 2 hour, 3 hour, up to 24 hours. So write down this. This is the definition or the objective function, problem formulation. Write down. If in the exam the question comes, formulate the hydrothermal scheduling problem, then you have to formulate this. So you have an objective function. See, objective function is the same. We have to minimize the fuel cost of thermal generators only. But the constants are different now. Now, instead of only thermal generation, we have got hydro and thermal generation which meet the demand. And also, the other constant is known as the water availability constant. The other constant is known as the water availability constant. Okay? And W summation means how much water in meter cube or million meter cube is available in the reservoir for that day. Okay. Now for this optimization, the time is divided into some scheduling intervals. Say K may be 24. So you can divide one day into say 12 intervals, 24 intervals, depending on that, and we optimize. Did you write? Now how to solve it? Now this classical method of solution we generally don't apply. We use various heuristic methods for solving this or many algorithms that I will show you in the next slide. But the general approach is, what is the approach? Lagrangian approach. What is the Lagrangian approach? You create a Lagrangian augmented function. How do you do that? How to create the augmented function? Objective function plus Lagrange multiplier lambda into constants. Objective function plus lambda into constants. Now here there are two different constants, two equality constants. One equality constant with respect to power balance and the other equality constant with respect to the water availability. Okay. So therefore in this case we have two Lagrange multipliers, two sets of Lagrange multipliers. One is known as the lambda k for the equality, demand equality or demand balance, and gamma known as the for the water availability. Okay. So just mention two sets of Lagrange multipliers are required, lambda and gamma. Two sets of, write down, two sets of Lagrange multipliers are required, lambda and gamma. Okay. Okay. Now what is the next step? The next step is obtaining the partial derivatives. Right? The next step is obtaining the partial derivative with respect to lambda, with respect to gamma, with respect to Pg. H and with respect to PGT. Okay. So all this you will find the partial derivative, equate them to 0 and solve it. So that is the approach. So in your exam, one theoretical question may be asked, formulate the hydrothermal scheduling problem and describe the Lagrangian approach to solve this problem. That's it. So it will be a 4-mark question. Okay. Okay. This is how. So as I told you, so you find the partial derivative with respect to hk, with respect to pk, with respect to lambda k, and with respect to gamma. Okay. This should be gamma, I think. This is gamma. Okay. With respect to gamma. Right? Okay. To solve the problem, we get partial derivatives as follows. Only write what I have highlighted. To solve the problem, we get the partial derivatives as follows. Okay. Right. Write down. Dou L by dou PHK, dou L by dou PTK, dou L by dou lambda k, and dou L by dou gamma. So these are the 4 equations that you will get and then solve it. Put a highlight for it. How do you highlight with the highlight? One below each. Don't write the complete expression, just write the highlighted words. This is the approach. We have an objective function, we have a state of constants. We create a Lagrangian by adding the objective function and the constant by means of Lagrange multipliers. Here we have 2 sets, lambda and gamma, because we have 2 sets of equality constants. What is that? First is the power balance constant, the second one is the water availability constant. Now what is the solution approach? Differentiate. Find the partial differential of the Lagrangian with respect to various variables. Thermal generation, hydrogenation, equality constant Lagrange multiplier, or power balance Lagrange multiplier, and water availability constant Lagrange multiplier. Okay, that is the approach. Next. Now, this is a typical system that I have solved. Okay. Can you tell how many hydro and how many thermal generators are there in this system? How many hydro is the solution I am showing you. How many hydro and how many thermal generators are in this system? One hydro, one thermal. Okay, you have only one hydro, one thermal. Okay. And this is the discharge given for hourly basis. So, from that particular hydropower plant, you have got this much discharge available throughout the day after taking care of irrigation, etc. Say in meter cube per second, 100, I think million meter cube per second. This one is a meter cube per second, small one, small item. And load demand for each of the intervals is given. So, what is given? You are given that you have got 2 generators. You are given the discharge, okay, and you are given the load. The question is, you have to obtain how much hydro should generate and how much the thermal. For example, it is 455, so you have to find out 235 will be generated by the hydro, and hence 455 minus 235 is equal to 231 to be generated by the thermal. Okay, and you have to also take care of the losses that will happen in this system. Okay, so the big problem. It's a big optimization problem, and you have to do it for 24 hours. Now, how you do it? This is the code snippet I have given you. So, in my GitHub profile, I have given this. So, here, not now, suppose for 5 years down the line, you are doing your PhD in power systems, and you have to do optimization. Optimization is a common technique now. Your main problem is something different, but you want to know how optimization happens with various tools. So in this, I have used MATLAB optimization toolbox, which has a function known as fminCon for nonlinear optimization. This is nonlinear optimization. Okay. So how it is there? So all this constant we give, and this is the load. It continues the load. Okay. Then I have got this Q max. Okay. Right. I start with some random values of generation. Okay. Initial. And I have got constants. Okay, this is the water availability constant. See here, BEQ is equal to WJ is the water availability constant. Okay. Now what actually solves this? That Lagrange multiplier or something. What solves this? You see here. This is the code or function which actually solves this. FMINCOM is a non-linear optimization routine in MATLAB optimization toolbox. It's a powerful tool. So I have used this. How it is done for around I think 12 hydrothermal systems, practical systems. I have done it and uploaded the code in the GitHub. So sometimes down the line or for anything you are doing and you want to see how optimization is happening using these toolboxes, you can see. It is also applicable for any other method you use because the approach is the same. Only this will change. Suppose you want to use Python, some Python function. Other things will remain same. Only this one will change. This optimization algorithm. Okay. So that completes the first part of today's class. The second part is